We are going to give 1 more minute so we can start the seminar of today. Thank you very much. On behalf of Dr. Branko Vers, Director of the Integrated Development Program and CIMMYT representative for the Americas, I am glad to introduce Nele Verhulst, who will present the seminar Field Research to Support Innovation in Agri-Food Systems. Nele was born in Belgium and earned a Bachelor and Master Degree in Bioscience Engineering with a specialization in land and forest management at the Catholic University of Leuven of Belgium. She obtained her PhD in Bioscience Engineering by the same university in 2011 and has been working as a researcher at CIMMYT since then. Nele is currently the Strategic Research Coordinator of the Integrated Development Program. She works on the development of conservation agriculture-based program practices and post-harvest technologies in Latin America, with a focus on Mexico and Central America. Capacity development with researchers and extension agents is also an important part of her work. Nele has developed a wide range of publications to communicate research results with more than 40 international peer-reviewed journal articles, 10 book chapters, and international conference proceedings. Nele, the floor is yours. Thank you.
Thank you, Isabel. Hello, everybody, and welcome to the seminar. I'm going to start today with a very brief introduction. I know that most of you are very familiar with these challenges, but I wanted to briefly highlight them to frame our thinking about cropping systems research. So, of course, our main challenge is how can we feed a world projected to have 9 to 10 billion people by 2050? And I'm sure a lot of you have seen the Eat Lancet report that came out last year that links, on the one hand, healthy diets for people with environmental sustainability and what we can achieve within planetary boundaries. Then, of course, there's climate change. Agriculture contributes about 25% of greenhouse gas emissions, while climate change is affecting agriculture through more extreme weather events, drought, flooding, and increasing temperatures. There's a large variability in greenhouse gas emissions among products, of course. If we compare, like you can see in the graph here, protein from beef versus protein from legumes. But also, if we look within the same product, we see that the impact can vary 50-fold among producers of that same product. So that indicates that we have substantial opportunities for mitigation. Then there's a biodiversity decline, mass extinction of species, and we know that intensification of cultivation methods to close yield gaps leads to a loss of biodiversity in agricultural landscapes and increases the pressure on natural diversity. This while at the same time, of course, agriculture needs biodiversity for things like pollination, biological pest control, etc. And then, especially working in Mexico as well, we know that they have very diverse production systems and that those different production systems have very different challenges. Going from specifically for Mexico, we have areas where we have very high yields and very high input use, but that input use has very low efficiency. So there we need to improve input use efficiency. And in the same country, we also have, of course, very low yielding areas where there's low use of inputs that is rapidly increasing and at low efficiencies. And there we tend to have higher crop diversity, more complex landscapes and rotations, and we need to find a sustainable pathway to intensification. So these are the core ideas, also inspired, of course, by those challenges that guide our cropping systems research. So our objective is to maximize overall utility rather than yield, because utility, of course, integrates yield and production cost and balances both and is very important for farmers. In this presentation and the results that I'm going to show, I'm not going to show a lot of results on utility, but I wanted to highlight it here that we are looking at that, especially in our more adapted research that really looks to concrete recommendations for farmers. Then a precondition for us to recommend a practice is that it reduces environmental impact compared to the current practice. We aim to reduce the use of external inputs as much as possible, which also goes, of course, to reducing secondary effects of those inputs and increasing utility of farmers. And we realize that the ideal cropping system is a moving target. New insights are coming to light every day, things that maybe we wouldn't have thought about a couple of decades ago in terms of environmental impact, for example, are very important today and are influencing, of course, the research that we are doing. So then to further give a little bit of context about fostering innovation through networks. So of course, the research that we are doing forms part of the knowledge hubs for innovation in agri-food systems. And here we can see the model, the theoretical model of what those knowledge hubs look like on the left. And on the right, we can see what that looks like in Mexico in terms of at the bottom, physical infrastructure in the field and the network. Well, just a very brief momentarily picture of an example of a network. So what that looks like in the field, if we go to the model here in terms of physical infrastructure in the field, we have research platforms. In those research platforms, we are looking at a certain cropping system, the limiting factors of that system, and what are the alternatives that we can test. So a research platform is an experiment where we are comparing farmer practice to several alternatives to give farmers information that they can use to make informed decisions about what technologies they want to use in their fields. Then we have modules in farmers' fields where farmers are comparing their farmer practice to a new technology that they want to try, and they are documenting all operations and the results of those operations. In extension areas, farmers are not comparing the technology, but they are applying a new technology. So around that physical infrastructure, we are building a network of stakeholders that includes, of course, farmers, but also extension services, researchers, buyers, input suppliers, government actors, etc., working toward a common objective of making those agri-food systems more sustainable. And I mentioned that in the modules, farmers are are choosing to apply a certain technology. And this is an example of the menu of technologies that farmers are choosing from. These are technologies that we have tested and we know work for a certain region. So the farmer there selects what technology they want to use in the field. So then moving on now to the core part of the presentation, about our research and the results of that research. So I'm going to start with the field-based research, and then at the end I'll say something briefly about post-harvest research. So we are doing field-based research in CIMMYT research stations, in long-term and component technology trials, in a network with local collaborators that you just saw the infrastructure that we have in the hubs. And we see conservation agriculture from the past research results that we've had as the foundation for sustainable cropping system. So that means conservation agriculture. If we look here at the figure on the right, the three basic components of conservation agriculture are soil surface cover. So that means that we either use crop residue or a live crop to cover our surface. Minimal soil movement, so that means that we will reduce tillage as much as possible. And the third one is crop diversification. That means that we will either grow different crops in succession, which would be crop rotation, or we grow different crops in the same field at the same time, which is the case For example, with the traditional cropping system here in Mexico, where farmers are used to growing maize, beans, and pumpkin in the same field at the same time. So those three basic principles of conservation agriculture we are looking at in our long-term experiments, but we've also realized that you could do those three things and not have a sustainable system if you're over applying insecticides, if you're using too much water, if you're not using your fertilization efficiently, etc. So that's why we have also component technology trials where we are looking at things like weed management, integrated pest management, nutrient management, water management, etc. To make sure that we are also making those components more sustainable so that we can have a sustainable cropping system. So we have research at CIMMYT research stations. We are working in Ciudad Obregón, where I am right now, up north, irrigated conditions, weed-based cropping systems, high input, larger farmers in general. And in central Mexico, we are working in El Batán and Toluca in rain-fed conditions. In El Batán, particularly, water is a limiting factor, as you can see in the picture here at the bottom right of the slide, where we had a severe drought in 2009, and we saw conservation agriculture on the left with high yields and very low yields in the conventional practice on the right. And this year in 2020, we saw similar pictures in the field, very dry conditions followed by frost at the end. So we have 6 long-term experiments divided over those 3 experimental stations. And then we have, as I mentioned, component technology trials where we are looking at nitrogen fertilization, weed management, seed treatments, genotype by system interactions, and identifying varieties for those conservation agriculture systems. Then we also have a network of research platforms that Simon Fontaine is coordinating. And there we have those research platforms at more than 50 locations in Mexico, covering, as you can see on the map, a very wide range of agroecological conditions and production systems. Those platforms are run by researchers from the national system or farmer organizations that we are advising on how they can put in practice an experiment and get some good information. We have a participatory design process for each platform with farmers, farm advisors, researchers, and other actors, like I already mentioned, really looking at the production system of the region, the limiting factors there, and what are the alternative technologies that we can promote or test. And of course, these platforms are part of the knowledge hubs, as mentioned earlier. So if we look at a couple of results now, first, I'll start, and I think that many of you have seen these graphs. These are long-term results from El Batán in central Mexico. So rain-fed conditions, and we have our maize yield on the left and our wheat yield on the right. So you can see that we started this experiment in, well, I'm saying we in the general sense here because I wasn't there yet, of course, in 91. And the value of these long-term experiments is that they allow us to really study long-term effects and look at things like stability, adaptability, sustainability of cropping systems, which are all things for which you need a long-term data set. And then they are also very important as training tools for researchers, farm advisors, and other actors, of course. Last year, in pre-pandemic times, of course, we received more than 2,000 visitors in this particular long-term experiment. So that shows how we are sharing those results, not just through publications, but with people in the field as well. So looking at the graph now, we see in green conservation agriculture. The squares are zero tillage, keeping residue, maize wheat rotation, and then I've added in the dotted line with the triangles, I've added a more diverse rotation. So that is a maize wheat bean rotation. And you can see that gives a slightly higher yield in some years. Then we are comparing that with our farmer practice in blue, which is quite the opposite. So that is monoculture, conventional tillage, and removing residue. And we can see that we have lower yields and with conservation agriculture. In some years, the difference isn't very big. And in other years, like 2009, if you remember the picture that I just showed you at the overview of the experimental station, where we had 2 tons per hectare in the conventional practice and 7.4 tons in the conservation agriculture practice. So then the last comparison is with what happens indicated in red if a farmer adopts zero tillage but keeps the monoculture part and keeps removing residue. And something very important here that we can see is that if farmers do that, if they only adopt zero tillage without the other two conservation agriculture principles, they have lower yields than with their farmer practice. And of course, lower yields than with conservation agriculture. We see similar results here for the wheat, although differences are smaller than for maize. Wheat is a little bit less sensitive to management in terms of yield. Then in the next slide, we are looking at results from irrigated conditions. And on the left, I put wheat yield from Ciudad Obregón, our long-term experiment at the CIMMYT station. And on the right, we have maize yields in Soledad Graciano Sanchez, which is a platform run by UNIFAP. And already since 96 as well, with a gap here in the middle where they didn't have resources to continue the experiment. So if we look at the results here, first for the wheat, we see irrigated conditions, so higher stability, of course, over years than what we saw in the rain-fed conditions. Then also the differences between our different practices are smaller. So again, we have conservation agriculture in green, the conventional practice in blue, which in this case is conventionally tilled beds incorporating residue. And in red here, we have permanent beds where we are burning the residue, and we see that that reduces yield compared to the conventional practice and compared to conservation agriculture, but nothing near as dramatic as some of the differences that we saw under rain-fed and dry conditions. And if we look at the maize results here in Soledad, we see in the first period, the green lines, which are permanent beds with different levels of residue retention, had somewhat higher yields, but especially here in the second period, we see higher yields in the permanent beds with different levels of residue retention compared to the blue lines and the gray one, which have different tillage practices. We see that the difference here in the second period is larger. That is when they used a higher yielding hybrid. So it was the conservation agriculture practice that could take advantage of that higher yield potential. Whereas in the conventionally tilled practices, the soil was severely degraded after so many years of tillage, very bad soil structure, bad infiltration. So after irrigation, it would take several days in the conventional practice for the water to infiltrate, leaving the crop in standing water, which is of course not good for the maize crop and results in lower yields. So this is just to show you a bit the range of cropping systems that we are working in terms of yield. So what we can see here are grade yield results from 20 research platforms in Central and South Mexico. And we see on the x-axis, we see the yield in the conventional practice, and on the y-axis, we see yield with conservation agriculture after at least 3 years of those different practices being in place. We see that the conventional practice yield ranged from 0.2 tons to 13 tons per hectare, so a very wide range. And on average, our maize yielded 0.85 tons per hectare more under conservation agriculture. Oh, sorry. So then we are going to look at a couple of soil health results. So on the left here, we see chemical soil health, and on the right, we see physical soil health. This is from El Batan, so in central Mexico, rain-fed conditions. Here, what I wanted to show you is the grouping of the different practices. So here we have 16 treatments, and we see that the zero tillage keep treatments with different rotations are grouped together. They had higher soil organic matter content, particularly, and then the conventionally tilled treatments. There's slight separation between the remove and the keep treatments, but they're fairly close together. And then we have zero tillage removing residue, three here in one quadrant, and then there's one that is very close to the zero tillage keep treatments. That is the wheat monoculture that is leaving more root biomass closer to the surface than if we do rotation with maize, and also a bit more standing stubble that we cannot remove. Then if you look at physical soil quality, we see basically the same grouping, in this case due to higher aggregate stability, better aggregate distribution in the zero tillage practices, keeping residue, which increases infiltration as well. And here the conventionally tilled treatments, keeping and removing residue, are mixed together. So for the physical soil quality, it doesn't matter much in this case whether we are incorporating the residue through tillage or removing it. We saw a similar grouping in our long-term experiment in Ciudad Obregón. So again, chemical soil health on the left, physical on the right. And here we are seeing in the chemical soil health our permanent beds retained, grouped together. They have a higher total nitrogen, higher soil microbial biomass carbon. Whereas our permanent beds, where we are burning residue, have increased sodium and electrical conductivity. And that is linked, if we look at our physical soil health, to reduced infiltration in those permanent beds where we are burning our residue. And those also have higher penetration resistance. So if we look at the physical soil health, we see in our conventionally tilled beds, high dispersion index, low mean weight diameter by wet sieving, but good mean weight diameter by dry sieving. So that means that your soil structure is good when the soil is dry, but that those aggregates are not stable, so they disintegrate upon wetting, and that means that you will have loose soil, clogging pores, and that reduces your infiltration. So that is why we see reduced time to pond here in those conventionally tilled beds. Whereas in our permanent beds, we can see that those where we keep all of the residue or part of the residue are just lumped together with high aggregate stability and high direct infiltration. So these are some results about carbon stocks in the soil from El Batan. Again, after 19 years this time of the long-term experiment, we measured carbon here at 0 to 60 centimeters, divided in different layers. So you can see that in the graph, you see 4 bars. These are all maize wheat rotation, and we have conventional tillage keeping residue and removing residue. And then the third one is zero tillage keeping residue, and the fourth one, zero tillage removing residue. And what we see is that in all layers, also the 40 to 60 centimeter layer, which is indicated in black, we have higher soil organic carbon stocks in the zero tillage keep practice. That goes back to, if you remember, the graph of the higher yield. So we have a higher yield in that practice, higher aerial biomass, and that relates, of course, to the root biomass that is contributing to those carbon stocks at the 40 to 60 centimeters depth. And here you can see the comparison also with the results again from those 20 research platforms in Central and South Mexico, with at least 3 years of conservation agriculture and the conventional practice. And here, if you're above the 1-1 line, that means that you will have higher organic matter concentration under conservation agriculture. And we see that that is especially the case at the 0 to 5 centimeter layer, which is indicated in red. But we also see that there is a lot of variability here, which shows also the importance of having that network of platforms to look at different practices under local conditions. And this is a similar graph, but for the soil structure. So we have mean weight diameter by wet sieving in red and dry sieving in blue. And we see, especially in the wet sieving, we see higher mean weight diameter in conservation agriculture, which is also, if you remember what we saw in our long-term experiments, conservation agriculture is improving, especially the stability of aggregates, which has effects, of course, for infiltration and the ability to buffer drought. So then I'm going to show you now some results that came out just a couple of months ago about bacterial community structure. So here we measured, again, in our long-term experiment in El Batan, after 26 years of 5 different practices. And what we did here that is different from most studies is that we took samples 18 times throughout the whole year when maize was grown and also outside of the cycle to complete the whole year. And the graph that you can see here are of soil properties throughout that whole year. So we have soil water content, organic carbon content, pH, and electric conductivity. And we see the white circles in those graphs are the zero tillage with rotation and keeping residues, or our conservation agriculture practice. You see that has higher organic carbon content, and you also see that we have a lot of fluctuation in all 4 of those soil properties throughout the season. And then if we are going to look at our bacterial community structure, we see that it also showed large changes over the crop cycle that were mostly determined by those varying soil characteristics, most importantly, water content and nitrate concentrations. So you can see here in the graph on the left that grouping more according to dates than according to practices. So our different practices are indicated by the different symbols in the graph. So we see that there were significant effects of tillage, of residue management, of crop rotation, but they were smaller than those fluctuations that we have throughout the season that were related to the soil properties that were fluctuating in all of our different practices. Then I often get the question, like, what is the application of this knowledge of our microbial community in the soil? And my response to that is, I think we are very far away still from a practical application of our understanding of the microbial community, because that understanding is still so limited, and it is very difficult to link these changes to functionality of microorganisms in the soil. But I have to say that where it has helped us to do these studies is that when we are getting a lot of questions about biofertilizer, for example, when people want to add microorganisms to the soil to affect the microbial community there, we haven't seen any consistent positive effects of that in some of those tests in Mexico. And I think that this work has helped us to understand a bit better why we haven't seen those effects. So then moving on to nitrogen in the grain. These are again some results of our long-term experiments. On the left, rain-fed conditions in El Batan. On the right are irrigated conditions in Ciudad Obregón. And I included in these graphs, again, some zero tillage practices in green, all with leaving residue, but with different rotations. So monoculture, maize wheat rotation, and the maize wheat bean rotation. And in blue, we have conventionally tilled practices where we have the monoculture removing residue as the blue diamonds, and then keeping residue in monoculture and the rotation. So if we look first at our maize results, we see that in some years we have higher nitrogen in the grain in conventional tillage practices. It is not significant in all years, but it is in some years. And we see for wheat even a bit more consistent results with higher nitrogen in the grain in our conventionally tilled practices. Of course, if you remember also from the graphs with yield results, we know that those conventionally tilled treatments tend to have lower yields. So that means that there's a concentration effect where you would expect some higher nitrogen in the grain through that effect. But if we look at Ciudad Obregón, where we have much smaller yield differences, we also see the highest grain protein concentrations in red here, so our permanent beds burning residue, and the lowest in the permanent beds where we are keeping all of the residue, especially in some years. The difference isn't as big in all years, but it is something that concerns us. Farmers in Mexico are not usually paid for quality or rewarded for quality when they are selling the grain. But of course, if you're looking at consumption, and especially farmers that are growing grain for their own consumption, it is important, of course, that we have sufficient protein in that grain. So it is something that we have been trying to understand, looking at nitrogen cycling in the soil to see what is going on there. I know also, and I want to mention that our colleagues in India, for example, have found the opposite. And at first glance, in some of the platforms where we have been able to take some data, we also don't see those results consistently. So we're not sure whether this is really a general effect. It seems not to be the case, but we would still like to understand why we see this in certain cases. So we have been looking at nitrogen cycling in a long-term experiment. This is a different long-term experiment from the one that I've been showing a lot of results of, because in this one we have bigger plots, so we can do a lot more destructive sampling, burying sensors and measuring devices, etc. So the practices that we looked at there were conventionally tilled beds, permanent beds where we were keeping the residue, and permanent beds where we were burning the residue. And we did two things there: an N balance in the winter, so that's a wheat growing season, our main growing season, and then a 15N study where we applied in a microplot fertilizer that was marked with 50N to track where all that fertilizer was going, and that we couldn't get that in time to start in the winter, so we started in the summer cycle with maize, and then followed our 15N also throughout the next wheat cycle. So if we look at some results here, so on the left I put some results of that N balance study, and on the right we see some results of the 15N study. And if we look first at the nitrogen balance, we see very briefly that it is positive in all of our practices. So that suggests that we are adding excess nitrogen to our system, which suggests, of course, that we should reduce those applications. But remember, there our dilemma is a bit, okay, so here we would say we need to reduce our nitrogen applications, but on the other hand, we have this problem with our grain quality that would suggest that we need to provide more nitrogen to our crop. So of course we need to find out what is going on there and identify the best way to get that nitrogen in the grain where we want it. If you look a little bit more in detail, our inputs are mainly coming, of course, from our nitrogen fertilizer, a little bit from atmospheric deposition and irrigation water, but really nothing much. And then our outputs, the way to read this is the conventionally tilled beds are in normal letters, then we have bold for our permanent beds keeping the residue, and italics for the permanent beds burning the residue. So here we can try to see, for example, that we had more leaching, apparently a little bit more in the permanent beds, keeping the residue. And of course, we had also some losses that that we measured as emissions. And then if we look at our 15N study, we are trying to see, so how much of that nitrogen that we applied as fertilizer can we still find? And first half of the graph is after the maize cycle, and then the second half is after both cycles, so both the maize cycle in the summer and the wheat cycle that follow that. And here we see that our permanent beds, where we are burning the residue, we're actually recovering the most of that fertilizer. It is a pity, of course, because that's not a practice that we can recommend, because we know, of course, that it is bad for air quality to burn the residue, and as we saw in the soil health graph, that it is also bad for your soil quality, for infiltration, etc. But that is where we are recovering most of our nitrogen, followed by the permanent beds with residue, and then the conventionally tilled beds. So I wanted to touch upon this. We have several component technology trials where we are looking at different methods of application. How can we do that in conservation agriculture to make sure that we get good grain quality? The results aren't very straightforward, so I haven't included them here because it would be quite a separate presentation to really go into detail. But something to look forward to once we figure that out. Then I wanted to mention also some results about weeds, which is of course an important topic in conservation agriculture, because when we are reducing or completely omitting tillage, we are taking away an important tool for weed management, which is tillage, of course. So here we can see results from the long-term experiment in El Watan. The graph is our weed biomass results, and the top half of the graph is with herbicide application, and the bottom half of the graph is without herbicide application. And then on the left we have our maize results, and on the right we have wheat results. What I marked for you in the graph is in green the conservation agriculture practice, so zero tillage, keeping residue, crop rotation, and in blue conventional practice, so conventional tillage, removing residue, and monoculture. What we can see immediately here is that conservation agriculture, we have the three components: reducing weed biomass, and especially when you combine all three of those. So that is good news, of course, in terms of our weed control. I must say here that, of course, it's our long-term experiment, so we have been on top of our weed control for the past couple of years. The main issue that we've had is in our weeds. There are some grass weeds in the monoculture treatments that we haven't been able to control well. So then, just to mention, we are looking at in a component technology trial at mechanical options for weed management. There's been a lot of discussion on herbicide dependence in conservation agriculture, so we are trying to see how we can reduce that, and I don't have a good picture of that, of how it worked in the field. We started with this last year, and it surprised me how well it was working, but more results there are forthcoming. Then another component technology is the use of compost. Compost can reduce the need for inorganic fertilizer, but of course it's usually incorporated through tillage. So we have an experiment where we have adapted machinery for the application of compost in conservation agriculture, and I'm showing some results here. We won't go into detail here, but the black is our control treatment without fertilizer. In red, we have only inorganic fertilizer, and the blue one is compost, and then the different purple treatments are combinations of 5 tons of compost as opposed to 10 tons of compost in the red treatment, combined with some inorganic fertilizer in the purple one. So top graph is yield. We see in some years the highest yield with the high compost treatment, in other years with the inorganic fertilizer. And we do see, if you look at grain protein in the graph below, we do see that that is the highest with inorganic fertilizer. So here we probably need a combination of both if we want to maintain our grain quality while using that compost that is available in Mexico. There's a lot of compost coming out of livestock systems that needs to find a sustainable use. Then also briefly here looking at genotype by system interaction, we've seen up till now soil health results showing that our conservation agriculture results in different environments for the crops. So the question was here, do we need to adapt genotypes to that? We focused on wheat in collaboration, of course, with CIMMYT breeders. The first thing we did was evaluating 48 genotypes from conventional breeding in conservation agriculture and conventional tillage. And then in collaboration with Karim Amar, we also evaluated almost 500 lines from parallel selection under conservation agriculture and conventional tillage to see if the selection had any effect on their later adaptation to both systems. So first, the wheat varieties coming from conventional breedings under different tillage systems. On the left here, we have bread wheat. On the right, we have durum wheat. We see that those two lines in full irrigation conditions and the two lines in reduced irrigation conditions are very close together, mostly overlapping even. So we had breeding progress in all systems. Genotypes performed similarly in conventionally tilled and permanent beds, and overall the genotype by tillage interaction was of little importance. And then, of course, the question remained, what happens if you do selection under zero tillage compared to selection under conventional tillage? So what we found there was that early vegetative growth was slightly improved with selection under zero tillage. So if that is an important trait, then breeders, of course, could select under zero tillage. The differences in yield between the two selection environments were marginal and in most cases not significant. We can see that in the graph here of grain yield. So we see in blue what was selected under conventional tillage, in orange what was selected under zero tillage, and then we have for 3 years the different environments, testing environments. So conventional tillage with reduced irrigation, and zero tillage. And we see in the first year some very small results that were significant, but overall not an important effect on our grain yield. So that means that if breeders would like to select under zero tillage, they can do that. It helps, of course, with more sustainable station management and with reducing costs at the station for land preparation. So then just to close off our field research results, something very briefly about the combination of conservation agriculture and agroforestry. Looking at more traditional systems of milpa, where in Mexico, as I mentioned before, farmers grow several crops in the same field. And there's a lot of agriculture on slopes with those small scale farmers. And there, the proposal here is, and something that has been promoted in Mexico, is to use fruit trees, rows of fruit trees in those fields on slopes, and the tree clippings and residues are placed in the tree rows to form barriers that catch runoff and gradually create terraces. So the question that we had here was, can we combine this system, it's called MIAF, and conservation agriculture, and we have 5 platforms that are testing this, and I'll very quickly show you some results of one of them in Santa Maria de Opuxco in Oaxaca, where we have avocado trees combined with a maize and a maize legume rotation. So here in dark blue, we see the conventional tillage treatment with maize fallow. And then especially here, if you look at the yellow and the light blue treatment, those have conservation agriculture, so zero tillage, and a maize legume rotation. So instead of the fallow here, we are using a legume. In the first years, that was 1 year of maize, and then the next year a legume that was beans. And in the last 2 years, it's maize in the summer and a legume, in this case peas, in the winter. So first, if you look at crop yield, we don't see a lot of effects of the different treatments. Just in 2018, we had the highest yield with the light blue treatment here that had conservation agriculture. If you look at net profit only of the crops, so not of the entire system, we can see that we have negative returns for the crops. So the crops that are grown here are most important for food security for farmers. This is the diet, of course, the staple foods in Mexico, maize, beans, and some vegetables. And we see even in 2019 a negative return for all of our crop during the summer, because we had a drought resulting in very low yields. But on the positive side, here, if you look at the net income from crops and those avocado trees, we do see a positive return in all of the treatments, and the highest one in the combination here, the last bars here, in blue for 2018 and orange for 2019 for the conservation agriculture combination with those trees. Then to close off, I just wanted to briefly mention our post-harvest results, and this research is coordinated by Silvanus Ojo. And here we are looking mostly at what is happening during storage, but of course problems during storage usually start before that, with insect infestation during drying in the field, late harvest giving more time for infestation. A lot of the shelling is still done by hand. Not all the grain is cleaned before storage. So we tend to have large losses of maize during storage. And here there is a study at 109 locations, a combination of research platforms and modules, going back, of course, to that model of the hub, storage during 1 to 12 months, and the technologies that were evaluated here with local collaborators and with farmers were hermetic technologies like metal silos and bags, some recycled plastic containers that were also hermetic, and also inert dusts. And what we see here, and I want to highlight here, the insect damaged grain. If you look in polypropylene bags, which is a common farmer practice here in the highlands, so above 2,000 meters above sea levels, those losses are still low. There we have generally low insect pressure, but below 500 meters above sea level, we have almost 40% losses in those polypropylene bags, whereas if we look at hermetic metal silos, losses are low both in lowlands and highlands. So the hermetic technologies were effective in reducing losses under farmers' conditions across agroecological areas and regardless also of storage time here. So there are, of course, aspects beyond storage that Silvanus is also looking at, and he's also looking at some other questions related to seed quality and grain quality effects during storage. But mostly we are confident about those hermetic technology. The technology exists. But the next question is, of course, how do we make it available and affordable for farmers, which is the question, of course, for all the technologies that we are working with, but especially for post-harvest, that has been an issue. And going back to close off a little bit too, that those knowledge hubs that we are trying to build a network so that we can get these technologies closer to farmers and so that they can actually use those. So just to conclude, these are our donors. I also included the references of the publications. And of course, you can always contact me with questions, and we still have 10 minutes left, of course, for any questions you would like to ask now.
Thank you, Nele. We have a question in the chat box that we received from Dr. Bruno Gerard.
Okay.
Says, nice work on genotype per environment per management. Work has been done on semi-finished or released varieties. Could we have a stronger interactions looking for key traits in a much wider genetic pool, pre-breeding stage? And are we missing some key traits as breeders and are selecting, as breeders are selecting under conventional practices?
Okay, so that is what we did in that experiment with Karim, where we looked at parallel selection, so selection under zero tillage and selection under conventional tillage, and we only saw an effect there for early vigor. So I would say that if that is a very important trait, then selection under zero tillage could give you an advantage. For other traits, at least the ones that we measured, probably not. I mean, it depends, of course, on, as you said, on the traits, on what pressure is present in your selection environments. But I would say in terms of genotype by tillage interaction, specifically that I don't think there's a lot there. I mean, we did a big effort, especially for wheat. No, I am not able to speak to maize because we haven't tried it out there. But I mean, so I think there's a point where you have to say, okay, I don't think it's worth it probably to keep investing a lot of resources in this when all the results that we've had so far say that there is not a lot of genotype by tillage interaction to be found. So it's probably better to focus on other things and to conclude, okay, so you can actually just do your selection under zero tillage if you like.
Thank you. Also, we invite you to open to raise your hand or to open your micro if you would like to participate, and to give any question or sorry for any question or any comment. I see one micro. No. Okay. Nele, would you like to give a final comment? Oh, yes, Matthew.
Matthew.
Right here. Okay, please, Matthew. Open your micro, please. Okay.
Hi, Nele.
Hi, Matthew.
Sorry, I came a bit late to your talk because another meeting went on too long. So did you comment anything about the disease issue? Because I know that often this comes up as a kind of excuse. And I'm just curious about if CA, it's a transient thing with the disease problem fusarium, or it's something that after a while kind of goes back into an equilibrium and has no more impact than if you were not using CA, if you see what I mean.
Okay, sure. I mean, we have those results from our long-term experiments because it's something that we have monitored extensively. I didn't present them here. Bram and Monica especially published some papers about that years ago, and it hasn't changed. I mean, we don't really see, and I know it's a question I get a lot. It's a question I get from all trainees, classes of trainees, and reliably during Visitors Week. And in the cropping systems that we work in here, we haven't seen that conservation agriculture increases diseases. So I think there, of course, the rotation is an important aspect. I mean, we do see that with maize monoculture, specifically, we get some disease issues, some pest issues, mostly, actually. But as soon as you get some crop diversification in there, we haven't seen any important issues.
So it's not nearly as big a problem as some people suppose then.
No, I really don't think it is. I think it might have come more from more temperate conditions where people are doing really long monocultures and are building up some disease pressure over time. But that's my assumption, and I've seen that a little bit in literature. And I think that way it got into the trainees, but as far as I can see in all the cropping systems that we are working in that are pretty diverse, it's more of a mind issue, if I can put it that way, than something based really on data.
Is there any evidence for any differences in root health or yeah, in relation to in general?
Not here in up north. I mean, there's very low pressure to begin with, so not here in El Watan. What we saw in the long-term trial is that you do get a little bit higher scores for root rot in conservation agriculture, but what we see there is water is our main limiting factor. So basically what we have in conservation agriculture is a much more developed root system that also has a bit higher incidence of root rot, and in our conventional treatment we have a much less developed root system that also has less root rot. But of course, in terms of your crop performance, I'd still pick the conservation agriculture one. And I think that is what maybe some pathologists that have these questions are very focused on that disease pressure, whereas I would say that our focus should be on our crop performance, because if you have a little bit more disease in those roots, in the end, if it doesn't affect your crop performance or your grain quality, then why would you care? I mean, I've heard people recommend burning because it reduces disease pressure. And then I say, well, it also reduces your yield. And of course, it's a problem for air pollution and whatever. But I think sometimes people are maybe looking at the wrong thing and seeing a problem there that isn't necessarily a problem if you look at the wider system.
Yeah, too many arsonists out there, right?
Yeah, true.
All right, thanks a lot, Nele.
Thank you.
Thank you. Thank you. And we would like to invite Dr. Martin Croft. He also raised his hand. Please, Dr. Martin.
Yeah, hello. Nele, I had to multitask a little bit, but I heard most of it, and I had to see on my my iPhone the slides. I would really like to see the whole presentation, but I'm very excited about it. There's not many of such valuable data sets. And one question for me is, did you work with crop modelers together? You know, when I would have time still for crop modeling myself, I would directly be in your office. Of course, COVID distancing, of course, to see what we can do together. Because I did the same with the IRRI long-term trials. There were all kind of magic stories about the long-term trials at IRRI for 40 years, that the yields declined and those kind of things that people said. It's because of radiation changes. And what I did basically is combine, do the modeling for that site. And you can do it for more sites, that you have the yield potential, which varies as well, that you basically can compare the yield gap over time and across sites and across the treatments. And then I don't know if you have enough data for also rain-fed plots, because if you have irrigated plots, yield potential is enough. But if you have rain-fed plots, of course, you need also the water balance models as well. But I think that working with a crop modeler on these data, and you know, crop modelers around the world that on academia that are really good, they would really love to work together with you on these data, because it's so rich. And the modelers are very often working a little bit in the dark in the modeling. Good data are always lacking. So but I saw on the slides, as far as I could see it, that there's really very exciting stuff in your data that's super important. And especially at Masagro, we are all, you know, hoping that Mexico keeps on supporting this great program, and otherwise we will do it in other countries. This is the type of research that we need. Long-term trials, that it's not 2 years is enough for a publication, right? But for the real impact in farmers' fields, and that's what you have been looking at. we need longer term data, more locations, but I think maybe modeling can add to it. Or maybe you worked already with our modelers, did you?
We did some work on modeling about 10 years ago. Back then, the issue was that, especially if you're going to those water balance models, that's an issue that they couldn't deal really with conservation agriculture as opposed to the conventional tillage very well. So we did some preliminary work, but we haven't continued it, and it's definitely something that we could look at.
Yeah, but at least weighing, because yield potential modeling, that's the easiest, that's the best, that's very well validated, no problem. And there you can already take out the radiation and temperature effects, so that you basically can exclude those effects of different sites and different years. Water balance, then this is a problem with conservation agriculture. Now, so much work has been done on conservation agriculture. Maybe we can get some of the crop modelers working on soil models as well, excited to make simple water balance models that also explain the difference with conservation agriculture. And then also that they find good payload transfer functions, because you cannot measure all the details of the physics of the soil, but we've been working always on payload transfer functions so that you have the standard data on that soil scientists collect on soils, and that you transfer those to biophysical parameters and things. And so maybe with the models that we have, Pequeño and other people, maybe Kindi, Ethiopia, that we have a short meeting to see what we can do, because, and maybe our people are maybe too busy, but then our people are too busy, definitely in academia, in Wageningen or in Queensland or other places, they might be excited.
Yeah, sure.
If I can be of any help, let me know, because I'm really feeling that I need some more time for science myself. It's exciting what you're doing.
Okay, definitely.
Okay, thank you very much. I would like to, we are in time already to finish. I would like to express our thanks to Nele for the presentation of this seminar, Field Research to Support Innovation in Agri-food Systems, on behalf of Dr. Brand Goberts, Director of the Integrated Development Program and CIMMYT representative for the Americas. So thank you very much, Nele, for this beautiful presentation. And remember, the seminar is posted in our CIMMYT webcast. And also we have a thank you note from Tania Casaya. Thank you very much for this information and support for our work with technicians and producers and farmers. So Nele, thank you very much for this presentation.
Thank you, and have a very nice day and evening, all of you. Thank you.
Thank you. Stay safe. Bye-bye.